Hello, everyone. So today we have Nicolas Hotton with us, who is doing the mathematics masters, and he's going to tell us a bit about random matrix theory. So I will leave the floor to him.
Yeah, so very good. So I will talk about random matrices today. So these are basically matrices with random entries. And in this talk, I will consider a specific model, but in general, you can consider many different types of random matrices. So this was first studied in statistics, where you're given some data which is random, and you're looking at the sample covariance matrix, and then you study the properties of its spectrum as the size of the matrix gets larger and larger. And this was also studied in physics, where you look at the Hamiltonian operator, and you study the eigenvalues of this operator for a self-adjoint, because it's a self-adjoint operator, so the eigenvalues are all real, and you study these properties. And this was studied by Wigner, a famous physicist in the 60s. So okay, so in my talk I will discuss a special kind of random matrices. So let me first define. So let n be a natural integer. Yeah. And then we study the matrix AN in Rn times n, where the entries are defined as follows. So we have AN ij. These are all distributed IID according to some distribution x for all I less or equal than j. And in this talk, we will consider only symmetric random matrices, and this is because we don't want to deal with complex valued random variables, and in this case, it's going to be the complex eigenvalues, which, since the matrix will be symmetric, all the eigenvalues will be real. Okay, and then AN ij is going to be equal to AN ji for all ij. Okay, so this is the setup, and then we'll assume some other things on the entries just for simplicity. So we'll assume that the entries are centered. So the expectation of Aij, this is equal to 0 for all I and j, and they also have variance 1. So expectation of Aij squared, this is equal to 1 again for all I and j. And since the proof we're going to use, the result we're going to state and the proof we're going to discuss is going to involve the moments of these random variables, we'll also assume that all the moments are finite. Yeah? So the expectation of Aij to the power k, this is finite for all k greater than 1 and for all I and j. Okay, so this is the context. So now we can do some small computations just to get started and to see a bit what are the properties of this matrix. So let me define first the eigenvalues of AN. So we call lambda 1 and lambda up to n, the n ordered eigenvalues of AN. Of AN. Okay, and now maybe we can ask first some simple questions. So what would be the expected mean of these eigenvalues? So okay, so what is the expectation of lambda 1 plus lambda n divided by n? So what would you expect this to be? Okay, since all the entries of AN are centered, and the distribution since all the entries are centered, then you would expect this to be 0, but okay, we can compute this. So this is equal to the expectation. And then what is the sum of the eigenvalues for a symmetric matrix? Basically, this is equal to the trace of the matrix AN. So this is equal to the expectation of the trace of AN divided by n. This follows just by the spectral theorem and the fact that the trace is invariant by orthogonal transformations. And now what is the trace of AN? So the expectation. Trace of an is just the sum of the diagonal entries. So it's the sum from I equals 1 to n of an I divided by n. And okay, as I said, like you just use linearity of expectation, and I assume that all these entries, they're centered, they have mean 0, so this is just equal to 0. Okay, so this is the first result about these eigenvalues. But now I want to discuss why, in order to be able to say something about these eigenvalues, you would need to rescale them basically. So we'll compute the variance of these eigenvalues. Okay. So what is the expectation of the sum from I equals 1 to n of lambda I squared divided by n? So again, this is a similar computation. So these eigenvalues lambda I squared, they are the eigenvalues of an to the power 2. And again, because an to the power 2 is symmetric, then this is just going to be equal to the trace of an to the power 2. So this is equal to the expectation of the trace of an to the power 2 divided by n. Okay. And now by the definition of the matrix multiplication, this is just equal to the expectation of the sum over I equals 1 to n, sum over j equals 1 to n of an ij, an ji. And okay, we divide everything by n still. And now we assume that the matrix is symmetric, so these quantities are the same. And they are n squared times this quantity, since we assume they have the same distribution. So this is equal to n squared divided by n times the expectation of an. Say, okay, 1, 2 squared. And we assume this is equal to 1. So this is just, okay. So this is just equal to n. And from there, we see that if we want to be able to say anything about the limiting distribution of the eigenvalues, we need to rescale everything by a factor of 1 over root n. Okay. This is the same thing that happens in the central limit theorem, by the way. Okay, so now we consider the matrix an divided by root n. And you want to study a random variable on the eigenvalues of that matrix. So let xn be distributed according to the uniform distribution on the the eigenvalues of an divided by square root of n. So let me introduce them. So lambda 1 tilde, like the order eigenvalues of an divided by square root of n. These are the eigenvalues of an divided by root n. Can you see? Okay. And then we also have the relationship that lambda I tilde, this is just equal to lambda I divided by root n. We just rescaled the eigenvalues for all I. Okay. And now the random variable we're going to look at is just the random variable which is uniformly distributed over this lambda I tilde. Lambda all the way through lambda n tilde. Okay. Okay. So why do we look at this random variable? Basically, so this random variable will be distributed over the real line. So, and as we've seen, this is going to be, I mean, the eigenvalues are going to be, they're going to have an average of 0, and then they're going to take value 1 over n every time there's an eigenvalue. So, okay, so maybe here you have lambda 1. Here you have some more eigenvalues. Here you will have more eigenvalues close to 0. and here you have lambda capital N. Okay. And so this is the first step. And now, basically, this eigenvalue, we want to study his distribution as like the distribution of this random variable that then gets large. And what we'll do is that we'll look at the bins and we'll plot the histogram of these eigenvalues for a large n. And we want to see what's the quantity of eigenvalues which will lie in some bin on the real line. So okay, so let me do some experiments so you can see what's happening. Yeah. So one might think that the eigenvalues will be a bit wild from this definition because okay, like I mean these entries they can take many values, but in the end you will see that there's actually some structure in the way the eigenvalues are distributed. So okay, so maybe I can show you some plots. Yeah. So okay, so to get started, maybe you can just generate a matrix of times 500 times 500, and we put it in, say, maybe 30 bins. Okay, let's see. How does this look like? So it looks like this. So you basically have some sort of, you can see like there's a shape appearing, and it seems like all the eigenvalues are they're in the interval -2, 2. So now let me take a larger matrix. So okay, maybe I take 1,000, and I look at 75 bins. Okay. And then it looks like even more like a semicircle. If I take even larger matrix, okay, something like this. Hopefully it doesn't take too long. Yeah, okay. Then it looks like this, yeah. So you can see there's really some nice geometric property going on, yeah. So that's the result we're going to discuss for the remaining of the talk, yeah. Okay. Cool. So now let me state the theorem I'm going to discuss. So the theorem is the following. This was shown by Wigner in 65, I think, yeah. And the theorem is the following. So for an divided by n as above, then we have that xn as I define. So this random variable xn. This goes in distribution to some random variable, which I'm going to call x sc, and sc stands for semicircle, as n goes to infinity. And what is this semicircle? So this is going to be where xc, where x sc is some random variable with density. With density P of x sc of x, which is just going to be describing the semicircle on the real line. Yeah? So this is equal to 1/2 pi square root of 4 minus x squared. 4, okay. I mean, it's the indicator that x is in -2. Okay. So it's just going to be the random variable distributed according to the semicircle you just saw on the simulation, yeah? Between -2 and 2. Okay. So this is rho egg SC. Okay, so now this is the result we want to show, but the proof is pretty involved, so I will only be able to outline the main ideas of the proof, and hopefully you will, hopefully the takeaway message is that there are some very nice arguments in the way you prove these statements, and basically there are many tools used in this statement which do not only rely on probability and linear algebra, but also on combinatorics. Yeah. Okay. So first, let me discuss what it means for a random variable to discuss to convert in distribution to another random variable. Yeah, I mean a sequence of random variable. Yeah. Okay. So in the simulation I did, basically what I said is that you will have that the ratio, I mean the number of 1 over n times the number of lambda I tilde, which are in some interval AB. This will converge to the integral from A to B of the density 1 over 2 pi square root of 4 minus x squared dx. Yeah. This is what I said orally. Yeah. But what I mean mathematically is basically that the proportion of eigenvalues which are going to be in this interval AB, they're going to converge to the integral over AB of the density of the random variable distributed according to the semicircle. Yeah. And so this is indeed the characterization of convergence distribution, but there are some other characterization, and the one I'm going to use for now is going to be slightly different. So I'm going to look at the test function. So we said that, so I'm going to say that xn, a sequence of random variable, then we say xn converges to x, in this case going to be SC, in distribution, if the expectation of f of xn, this goes to the expectation of f of x SC for all nice f functions. And what I would mean by nice is continuous and bounded for all f continuous and bounded. Okay. So now this is our new definition of a convergent distribution. So this definition might not look familiar to you, but I mean these two definitions are actually equivalent. Yeah. Okay. And so now how do we proceed? So we've seen by the plots, and this was hinted to us already, that most of the eigenvalues are going to lie on this compact interval minus 2, 2. And so by this argument and the fact that, I mean, by the combinatorics of the problem, basically the eigenvalues cannot be too far away from minus 2, and they won't also be like too far away from 2. So in general, like the largest eigenvalue is going to be very close to 2, like maybe somewhere here, and like the smallest eigenvalue is going to be somewhere here, and then one can actually show that as n gets large, then like the largest eigenvalue will converge to 2. But okay, this is another problem that I'm not going to discuss. And so by this heuristic, one might actually be tempted to say that this integral, this expectation, is actually very close to another one, which is the following, which is the expectation of f of xn, and I restrict this to some compact interval minus k. Okay, and this case I just take it large enough so that most of the eigenvalues will lie in this compact interval minus kk. And then I want to show that, okay, like, so this will be very close to this, and this is already supported on a compact set, so then this is the same thing as saying that this goes to the expectation of f of x SC, indicator of minus k. Okay. And now we have a continuous bounded function on the compact interval. So by the Weierstrass approximation theorem, we can approximate it with polynomials. And then what we see from this argument is that it would be good enough to show that if the test function is a polynomial, then this converges to like a polynomial of the random variable x semicircle, then we will actually get convergence in distribution. So then, okay, we can approximate f by polynomials in polynomials, and so we want the expectation of xn to some power k. So okay, this k is going to be different from this k I chose for the compact interval. This goes to the expectation of x semicircle of k for all k greater than 1. So yeah, so if you want to show it for polynomials, then it's good enough to show it for every monomial, and then you will get the result. You know? And what is this in the case of our problem with our random variable xn? So this is just equal to the sum from I equals 1 to capital N of lambda I to the power k divided by n. Because okay, like it's just a discrete random variable, so this expectation is just equal to this. And you want to show that this converges to this as n gets large. Okay. But now what I'm going to do is not exactly this, because you don't have much control on this quantity, but I can look at the expectation of this quantity. And okay. So a result which I'm not going to state, but it's actually a true result, is that like this quantity will be very close to its expectation. And why is that true? Is because like in probability, if you look at either a lot of random variables or in very high dimensions, then for such a sum of random variables or for such a large number of eigenvalues, for them to be very far away from their expectation, if they still have some level of independence, they would need to all collaborate to move in some direction. And if you're in a very high dimensional space, like here we're considering like very big random matrices, then this is very hard for them like to all move in the same direction, since they still have like a high level of independence. So this is the argument. So okay, to justify what I'm going to show. Well, what I'm going to show is that the expectation of lambda 1 to the k plus lambda n to the k divided by n, that this goes to the expectation of x semicircle to the k for all k bigger than 1. Okay. So now we have to compute this quantity. So let me do it on a new board. Yeah. Where is the? Do you see the? Where? In the SIG, okay. Yeah. Okay, so let me just, maybe for now, let me just erase this part. Okay. Very good. And it's good that I keep this part because the argument will be the same. Okay. So I want to compute this quantity. Okay. So I have expectation of the sum from I equals 1 to n of lambda I to the k divided by n. And then what is this equal to? Again, the lambda I to the k, they're going to be the eigenvalues of an to the power k. And since an to the power k is symmetric, then this is going to be equal to the trace of an to the power k. So this is equal to the expectation of the trace of an to the power k divided by n. And now, okay, again, by the definition of matrix multiplication, here we did it for the case k equals 2. But for a more general k, this is going to be looking a little bit worse, but actually it's not. I mean, there's nothing crazy happening. It's just matrix multiplication, so okay. So it's going to be the following. So over all indices A1, AK, ranging from 1 to capital N of the, okay, let me keep the expectation here for now, of A n I1, I2, A n I2, I3, all the way from A n Ik, I1, and I divide it by n. Okay. So this is how it looks like. So now I realize that there's something that there's a small notational problem. So here the lambda as I wrote, like this is like in my previous notation, this is lambda I tilde. So these are like the rescaled version of the lambda i's. Like I hope this doesn't disturb anyone. Like otherwise I will clarify this again. And okay, like this an, then I forgot something. So this is divided by n, but then there was a rescaling. So the rescaling is the following. So I had I rescaled by root n, and then I put it to the power k. So this is like root n to the power k. And okay, here this is just going to be 1 plus k divided by 2. Okay. So now I can move the sum out of the expectation. I can move also this factor n to the power 1 plus k over 2. So I have 1 and 1 plus k divided by 2 times this big sum. Oh, and this is I1 Ik times the expectation of this big product AI1 I2 then AI1 I2 I3 all the way through AN AIK I1. The reason why the last one is I1 is because I'm taking the trace, so all the quantities that would be on the diagonal of this matrix A n to the power k. Okay. So now we already have some expression. So there's one thing that we can realize straight away is that okay, so these are all going to be copies of X because like okay, these are all entries of the matrix AN, and these are copies of X, and they might be different and they might be the same. So this one is, this one we can call it X1, and then this one either it can be another independent copy, so it can be X2, but it can also be X1. Okay. If these indices match. Okay. And so we have like several copies of the random matrix of the random variable X to some power, because okay, the common terms will multiply each other, and if k is odd, then you will be able to factorize a term x to some power to some odd power, and this will be 0 because we assume that that the random variable x is centered. Okay. So then, let me write this remark for k odd, then this quantity I'm going to call it delta nk, delta nk, this is equal to 0. And okay, let me re-say the argument. Let me say the argument again one more time. It's like basically if you don't if you don't have this element to an odd power, then they will all be to some even power, and then you will have an even number of them. But we assume that we assume that k is odd. Okay. Okay. And now for k even, this is more interesting because you will have some pairings of them, and then you will have them at some even power, and then they won't cancel anymore. But the one that will cancel is the one where they will still appear at some odd power. So for example, let me look at the example. K equals 4. And if I have the term, so I'm going to have the term, for example, an 1, 2, an 2, 3, an 3, 4, an 4, 1. It's okay. So if you have this term, then all these terms, they're independent, and so this will just be equal to 0. Yeah? So the only such expectations which won't be 0 will be the ones where you actually have pairings of them. So where this random variable will be the same as one of the other remaining random variables, and the same goes for all the other ones. So we only have to look at pairings. So let's keep studying this case, k equals 4. So in general, the term will be like this. I1, I2, and I2, I3, I3, I4, and I4, I1. Okay. And now, what are the pairings you can make? Is okay. Like, I'm going to denote these entries by nodes. So you have this node. So this one can be equal to this one. You have this, and then this one is equal to this one. You have this. Or this one is equal to this one, this, and then this one is equal to this one. You have this. And the only pairing that remains is this one is equal to this one, and this one is equal to this one. Okay. And now let's see what are the constraints of these pairings on the entries. So basically, if I have this pairing, then by symmetry, okay, so I have I1, I2, and this is supposed to be equal to this entry I3, I4. So then I have basically I have I1 is equal to I4, and I2 is equal to I3. So I have two constraints. And then this pairing, what do I have? So this pairing, okay, by symmetry, so I have I1, I2, I2, I3. So the only constraint I have is I1 is equal to I3. And here the constraint is the same. And here for this pairing, then okay, look at, so it's AI1, I2, and then AI4, I1, and then by symmetry, the constraint will only be I2 is equal to I4. And the constraint will be the same here. Okay. So now we see that there's a bit of combinatorics happening in this problem, and we see that when these pairings don't cross, then they are less constrained, and when they do cross, it seems like they are more constrained. Like you end up having more constraint on the indices, yeah. And this is actually very important for this problem, because now we need to know what are basically the number of such non-crossing pairings. Because okay, like when there will be, I'm not going to give a very precise proof of such a statement, but basically what happens is that all these non-crossing pairings, you will have less constraint, and you will have exactly basically, okay. So for non-crossing pairings, we'll have exactly k divided by 2 minus 1 constraints. And for the other, we will have more. The other pairings, we have more. So, okay. And then what does it mean to have exactly k divided by 2 minus 1 constraint? It means that you will have, so here you have like, so here you have like n to the power k different choices of indices. And then since you have like k divided by 2 minus 1 constraint, then this means that you will have basically k n to the power k minus, okay, k minus k divided by 2 minus 1, three variables. and this is just n to the k divided by 2 plus 1. Okay. And basically, since you're dividing by this, this will tell you that the leading term of this big sum is only going to be the non-crossing pairings. Yeah. So then what we have is that delta nk, this is equal to the number of non-crossing pairings plus a big O of 1 over n. Okay. And now this is where some very interesting combinatorial quantity comes in, and this is going to be basically the last surprise of the talk. So what is this number of non-crossing pairings on the k elements? Yeah. Because okay, like we assume that k is even, so it makes sense to do this. So I'm going to call this quantity c k divided by 2, and this will be clear in a second why I divide this by 2. So the statement is that c k divided by 2 is the k divided by 2 Catalan number. Yeah. Okay. So why is that so? I mean, let's look at these pairings. So, okay. So we have k nodes. And this is going to be L, this is 1. And then this is k. And you're making pairings. So what is the friend of 1? So the friend of 1 will be L. And then we can make a remark is that L has to be even. Because, okay, we are looking at non-crossing pairings. So all the nodes here, they cannot be paired to nodes here. And same thing, like all the nodes here, you cannot pair them here. And since k is even, then here you need to make pairs, so it's going to be even. Here it's going to be even, so L has to be even. So, okay, so L is even. And now we want to find the recursion for ck divided by 2. Okay. So what is ck divided by 2? This is just going to be equal. So basically, you take all the possible values of L. So okay, L. Yeah, all the possible value of L, and then you're looking at the sum from L equals 1. I mean, okay. Yeah, it has to be even, yeah. I mean, from 2k. Yeah. This is good, yeah. I mean, okay. I think the best way to write is yeah, right. You write L is equal to 2j. And then this is the sum from j equals 1 to k divided by 2 of cj, cj minus 1 times c k divided by 2 minus j. So what is the case? Basically, you take all L, and then you look at all these pairings here. So the pairings here is going to be, I mean, like if I take L is equal to 2j, then basically you have this number of non-crossing pairing here, because like this pairing they don't cross all over here, and then this quantity is going to be all the number of non-crossing pairing here. Okay, so I hope this is clear. And what is this recursion formula? And then okay, like what is the number of non-crossing pairings for 0, like C0? Then I mean, it's only the trivial pairing, like there's nothing to do. And then for a C equals 1, then you have to know there's only one pairing. And then this recursion formula is exactly the recursion formula that you get for Catalan numbers. So then, like, we conclude that that Ck divided by 2 is the k divided by 2 Catalan number. Yeah. And there's even an explicit formula for them, which is not so relevant, but I mean, we have the following is that, so in general, Cn for the nth Catalan number is equal to 1 over n plus 1 times 2n choose n. Yeah. Okay. And now there's only one thing left to do. So this is good that we have this here. Yeah, this is good. So let me erase this. So let me repeat what we have shown. So we have shown that that this quantity delta nk is equal to c k divided by 2 plus little o of 1 divided by n for k even, and this is equal to 0 for k odd. Okay. And so now what was our original strategy? It was to show this. But now I have to tell you about these moments of the semicircle. So let me write it as a proposition. So proposition basically is going to be the following then. The expectation of x semicircle to the power k, and what is this equal to? It is equal to the integral from -2 to x to the k square root of 4 minus x squared divided by 2 pi dx, and this is equal to, that's the proposition, 0 for k odd. I mean, this is obvious since the distribution of the semicircle is symmetric. So if you take an odd moment, it's going to give you 0. It's going to stay centered, and it's going to give you c k divided by 2 for k even. Okay. And this proposition, I'm not going to prove it because basically it's just. I mean, you can use any integral solver that you like the favorite one, and then you plug this integral in, and you will be able to see that this is true. Okay. Or otherwise, you can just do it by integration by part, but this is quite tedious. Yeah. Yeah. And so in the end, what we have shown is exactly that this quantity of the expectation of this trace of a n to the power k goes to the expectation of the moments of the semicircle. And if we go backward, then what it means is that I mean, we will have shown that this empirical spectral distribution of the eigenvalues, then if you look at this definition with the bins, then this is true that this indeed converges to this area under the semicircle. So I hope you enjoyed it, and yeah, this is one of the main results in random matrix theory. And obviously, I didn't provide all the details, but I hope I provided the main ideas. And if you want to know more about this, then maybe you can ask me or check the details later on if you're interested. Yeah. Thank you. Yeah. I mean, you can consider, for example, the maximum of the eigenvalues. Like, I mean, if you consider, you can consider, so not xn, but yn, which is going to be equal to the max of lambda 1. This is also a very interesting quantity, and then you will be able to also have some nice statement about this random variable, and this is also an important quantity for applications. If you're not looking at necessarily matrices with such simple entries, but maybe you're looking at sample covariance matrices, and you want to look at what's happening for the largest eigenvalue, maybe. I mean, if you're looking at these signal models, then this is a very important quantity in that case. Yeah. Or maybe you can look also at even more exotic functions of the spectrum, yeah, depending on the problem you're interested in. Yeah.
And is this like speed of convergence kind of tight?
I mean, the speed of convergence is yeah, it's tight. Yeah, I mean, because basically, I mean, but then like to be able to compute exactly what's happening for these non-crossings, like this is again quite tedious because you will have. I mean, you need to use this assumption you had on the condition that the moments are bounded, and then you need to be able to count when all these constraints happen, and then like from this you will be able to bound it in this way. Yeah. Yeah. Is there any other questions, or we go to the apéro? Yeah.